that I actually approached this assignment of giving some sort of survey about the Langland's program, about what sort of progress is being made, with great trepidation, because it's very vast. And I tried to write 3 different versions of it, and the first one was rather technical and perhaps appropriate for those who are close to the field, and the final one I ended up with is very down to earth and hopefully approachable for other people. And so perhaps not so suitable for people who are experts in the field. So you're welcome to turn on silently your Blackberries and check your whatever. Okay, so I want to start. So one of the facts I do like about automorphic forms is they show up all over the place. And maybe there are several examples one could give, like the Sato-Tate conjecture, which was discussed a lot in the previous one. I enjoyed watching those videos. So I will start with one problem that perhaps people know. Oh, do we have white chalk or is yellow preferred? Okay, all right. All right, so I want to start with a problem that people may be interested in, and important progress was made by the work of Kim and Shahidi, so I want to start with that. So I will write H for the upper half plane, and okay, and so what do we want to do? So you pick some positive real number, and you pick Z and W in the upper half plane. If you like, you can take W to be I if you want, and then you take a gamma. I'm going to take it to be a congruence subgroup of SL2Z. The problem can be posed, of course, for any Fuchsian group, but you can make progress mainly for this case. And for example, you could take gamma. In the whole talk, you could take, in a sense, gamma to be gamma 0 of n, A, B, C, D, in SL2Z, such that C is congruent to 0 mod n. So that's a very beautiful group to work with, and it's kind of ubiquitous. It comes up all over. So now we can look at P of x to be the cardinality of all the gammas in gamma, such that, let me write down the formula and then I will say what is going on. You take gamma of Z. By the way, gamma acts on the upper half plane, of course, by the standard form. Gamma Z is just AZ plus B over CZ plus D. So you take gamma Z minus W. W is something. Z and W are fixed. And then I'm going to divide by the imaginary part of gamma Z times the imaginary part of W. And then I take all those things for which this number is less than or equal to x. And then you take the cardinality, the number of such things. So essentially what it's computing is, it's kind of computing the number of lattice points so inside a hyperbolic circle of radius x centered at W. Okay, so you take these things here. Excuse me. Yeah? Thank you. Oh, all right. Okay. All right. I'll switch to white because I'm used to it. Okay, so again, this thing here comes from the fact that you have the hyperbolic metric, and if you write down the distance between Z and W, you know that take the semicircle and you have 2 more points on the real line. You take the logarithm of the absolute value of the cross ratio of the 4, and you work it all out. You essentially get this. And the point is that the theorem, so this now is due to the work of Kim and Shahidi. I think it's a very beautiful result. Not many people seem to know this. So they proved that P of x is equal to by the way, this 2 may have to be 1 if minus 1 is not in the group, so I will ignore that. And then you take the area of H mod gamma divided by this times x, and then plus rho of x to the 2 terms. So hopefully I'll get to say something about why this is true a little later. But I just wanted to put it up so that it's kind of a very natural problem. Of course, everybody knows about the usual circle problem in the Euclidean plane. And this is analogous in the hyperbolic setup. And it's very beautiful. Okay. So I will come back to it later and then explain why this is true. Okay. I just wanted to put up something to start with. Okay. So the point is that I want to say something about automorphic forms. And so anyway, the classical things that people study are modular forms. And of course, this kind of became a big giant called automorphic forms. And it's kind of like Los Angeles pre-1900, and this is like, no. it's a megalopolis. Okay, so everybody knows about this. So I won't actually give a definition and so on. So essentially, well, maybe I will say very quickly, the classical holomorphic modular forms are exactly those which satisfy the property that f of gamma z, if gamma is like this, it's cz plus d to the k f of z. And then you want f to be also holomorphic at the cusps. And then it's called a cusp form. Means f in fact vanishes at the cusp. And for those who are not very much used to it, just think of the case when gamma is, say, SL2Z. Then all these actions are spanned by two actions. Z goes to Z plus 1, and Z goes to minus 1 over Z. And so if you take a modular form, the first one allows you to write it as a Fourier expansion, an q to the n, where q is e to the 2 pi I z. And that encodes the first transformation that is invariant under Z goes to Z plus 1. And this sort of arises in all over the place. So this is kind of in combinatorics to arithmetic, algebraic geometry, to various places, you get Q expansions. So it's kind of very nice to know. And then what is not clear is that the non-obvious thing is that f of minus 1 over z is this times f of z. So this hidden, so this is what I call hidden symmetry. In a sense, when you have such a Q expansion, the first one is easy, but the second one is not. So that's actually the study, in a sense, of all the theory of automorphic forms, even a lot of the complicated ones involving converse theorems and various things, have to do with the same principle, is that they're invariant under certain simple transformations like Z goes to Z plus 1, but there are other things that are non-trivial that you want to understand. And that is quite difficult. And so maybe I should give, so the standard two examples, whenever somebody wants to learn about modular forms, I tell them to understand the following examples. One is the delta of Z, which was studied by Ramanujan, which is Q goes to 1 minus Q to the n to the 24. And it has a famous expansion. If you write it this way, maybe I'll call it M here. So this M and N are different. And this is a cusp form. And this is a unique cusp form of weight 12 for SL2Z. And because after you hear talk about modular forms, you should know some examples. And so the second example is G of Z. So I could now take Q. I could take Q to the M squared minus Q to the 11M squared. And this is another very important example. And this turns out to have weight 2 for gamma 0 of 11. In fact, in this case, the upper half plane modulo gamma 0 of 11, if you compactify it, and sometimes call x 0 of 11, and this is an elliptic curve in this case, which is in fact defined over Q. And in both cases, what happens, one of the ways to study that prove that it's modular, there are many different ways to prove them, actually. One standard way that you learn for this is to relate it to Eisenstein series and so on. But one of the ways to prove this modular is to look at the L functions. And you take these Fourier coefficients an, you just take an over n to the s. And what happens is that this L series, one sees that this thing here, just like the Riemann zeta function, this LSF converges in a right half plane, and in fact the real part of it, okay, and satisfies a functional equation and analytic continuation to the whole plane. So, which is not obvious, but if you can prove such a thing, so this, in some sense, kind of encodes the modularity. In fact, Hecke knew for SL2Z already that being modular in the sense that having the certain symmetry is exactly equivalent to the L function having these good properties. And one has to be very careful with the functional equation and what exactly you have to do, because you have to add, to get the functional equation, you have to also add certain gamma factors. And in both these cases, depending on how you normalize them, you get gamma of s, and this is essentially gamma of s over 2 times gamma of s plus 1 over 2. It's very important to know what it is. So let me give you a third kind of example. Just okay. So this is a strange example, but you can take phi of q to be q to the minus 124 n greater than or equal to 0, q to the n times n plus 1 over 2 over 1 plus q up to 1 plus q to the n. And then you take plus, sorry, here there's no minus, 1 over 24. You can, of course, expand this in terms of, so if I remember correctly, you also have n twice, n greater than or equal to 1. Then you get minus 1 to the n, q to the n squared, over 1 minus q, up to 1 minus q to the 2n minus 1. So you can look at this q expansion, and you can formally write it down, write it as some series, n and z, as a q series, some an q to the n over 24 here, and then n is congruent to 1 mod 24. I'm giving you a very explicit example. So if you take this example, and you can actually, in fact, associate to it an L series, which is like this, an over n to the s. This has all the nice properties of the same as the above. This has actually have analytic continuation and functional equation. But it's not a holomorphic modular form. but it's not a holomorphic modular form. And the way you see it, one way to see it, there are many ways to see it. One way to see it is when you look at the functional equation, actually instead of this gamma factor, you get gamma of s plus 1 over 2 squared. It's just that actually it corresponds to a real analytic modular form. It's called a Moss form with eigenvalue lambda equals 1/4 attached to a character, an ideal class character of q squared root of x. And it's just written in this form. And this example I took out of a paper of different people who have studied these mock theta series. And the one that's nicely written about this, Henri Cohen's paper. So it's what is really interesting is that the right modular form for this is not this, the way you should write it actually as phi of q, but instead the right modular form, well, of course, it's not a modular form in the classical sense, is something like f of z, so what you do is that you have to essentially take n in z, n not equal 0, then you take a n, you take the same a n's, and then you divide by the square root of n, and then you have to take a, I think I'm going to mess it up but by writing the exact thing, but here what you have is a k Bessel function. So this is a k Bessel function. And it's kind of interesting that you started, so sometimes you may start with a q series. It looks like a modular form in the usual sense, but it's not in the usual sense, but it's something more complicated. So this is what is called the Moss form for gamma 0. I think it's 1152. It's referred to a character associated to the q squared root of 6. And Laplacian eigenvalue. Lambda equals 1/4. Okay, so in a way, there is a very compact way to study them both together. In some sense, it's good to sort of think of the adels of Q, which you take to be the real numbers across all the prime numbers, or finite primes, and where you take some restricted direct product of QPs. So you take these here, so this is the adel ring of Q, and as a group, it's a topological group, locally compact, and inside it you have Q embedding discretely as a lattice, meaning so it's discrete and co-compact, and this adels modulo Q, which is sometimes called the infinite solenoid, and that's because this is really an inverse limit of R modulo nz. So you can think of it as the S1, and you take all the degree n covers, and you take the projective limit of all the degree n covers. And so the adelic way is to actually study all different possibilities in a sense simultaneously. It's a very useful device. If you don't like it, you can always go down to a particular level, but sometimes it's more work, even though it may be more understandable what happens here. So what one does is that one actually looks at kind of L2 of, in this case, GL2Q. So let me, for simplicity, assume that, in fact, so let's take GL2. Of course, you also have the center, the scalar matrices. For simplicity, I will look at the case. This is like taking the things of character 1 and take GL2 of the adels of Q. And one looks at this, actually, and the GL2, the adels acts by right translation here. And if you like, this is analogous to, this is just a jazzed up version of L2 of SL2R modulo gamma. Okay. So, and the point is that just like here, this thing here is non-compact. Same over there, but at least it has finite volume. And it's the same thing here. And what one can do is one can look, if you look, call this V, the space, V has a discrete part and a continuous part. And then the discrete part contains the things of cusp forms, the analogs of, I won't define them, it's exactly like making the zeroth Fourier coefficient vanish. That's all. Action of this group as unitary representations. Yeah, so direct, yeah, so this is a, so to be precise, you should put the Hilbert direct sum here if you want. And so this is a representation as unitary representations of G. And I won't define this. This is kind of non-trivial to show that the space of cusp forms is actually in the discrete spectrum. And in fact, you could do everything here. In fact, with GLN, I just replace 2 by n. And it's still an analog of this. So it's all true. And in fact, maybe I should mention here that since we are giving a, since you have given a prize to Wolfsburg, I should say that the V discrete, in fact, has 2 parts, the cuspidal part and what is called the residual parts. They come from residues of Eisenstein series. And this was described, I'm not going to write right now, this was described by a beautiful theorem of Mogla and Wolfsburg. And it's one of his best theorems, I think. We use it a lot. Okay, I won't touch that because I have to come back to it eventually. If I can locate the eraser. Is there an eraser? Oh yeah, I got it. Thank you. All right. Okay. No. Oh, okay. Maybe I should go ahead and, yeah? No? I may look like I do, but that's the constant state of mathematicians. Okay. Okay. No, it's just that every time I give a lecture somewhere, they have a different thing. It's not uniformized like Bourbaki style of blackboards. Okay. All right. So anyway, before I say something more general, I want to say in very roughly, functory. So the principle of functoriality of Langlands, which is a central thing, it kind of predicts the transfer of automorphic forms or modular forms on a reductive connected reductive group G, let's say over Q, or over more generally a number field or a function field over a finite field. So I will discuss number field, there has been great progress in function fields due to Laforgue, and I will not discuss that. So from 2 to another, to those on another. And to be precise, we want, maybe it's simpler to say the quasi-split group G prime whenever there exists some. And this is a homomorphism between their dual groups. So there's a, and this is often denoted like this, and I'll come back to it in a second. So this dual group is has a complex productive group G check and the action by the Galois group, photograph, and this G check is this is associated to the dual root down of G. And so this is a complex reductive group. And for the first time, you could always think that, so think, if you like, you can, so it's easier cases when G is split. If G is split, it's easier. Or at least if G is, you can always take the reductive group and look at its quasi-split form. And if the quasi-split form is, so if you take any group G, you can associate to it a quasi-split group. This means it has a Borel subgroup defined over the field. And if this G star is split, this is easier in that you don't have to, you get a direct product. And then in some sense, for many reasons, you could forget about the Galois action. So that's always the first thing to do. For example, for G equals GLN. I should tell you that I'm supposed to write a report about this. I'm not as organized as Jean-Loup, so I'm still writing it. So hopefully, whatever I don't define, I will try to define in my notes. I mean, even that may be difficult because 20 pages is hard. It's a bit like... So, all right, so now go back to this here. When G is GL2, so again, this is kind of a complicated way of looking at it. So in some sense, if you think of automorphic forms as those exhibiting hidden symmetries, what he says is if you start with one group or one space associated to the group, and if you have something that exhibits these extra symmetries, then there are corresponding ones on the other side. This is not at all obvious that you have this. You know, so a simple instance is if you know, say for example, G is GL2 over Q, and then and then you could look at the symmetric power, or let me even say that so you could look at the symmetric power representation. And in this case for GLN, before I go on, I should have said here that if G is GLN, then the dual group is, this is actually in the split case, and G check is also GLNC, which is a very special, so this is very special. If this always happened, you wouldn't need to define functoriality, but if you take the odd orthogonal group, then the dual is a symplectic group, and vice versa. And if you take the even orthogonal group, then it's solved. So the symmetric power representation is one example where you take GL n plus 1 C. So this is the n plus 1 dimensional representation. And then it predicts, for example, that if you take a automorphic form pi, and now in the GL2 case, as we saw before, there are really, over Q, there are two possibilities. One is either holomorphic, or it's of the Moss type. And it tells you that actually you have something called sim n of pi. And this is supposed to be an automorphic form or on GL n plus 1. Okay, and this is still quite open. Since I mentioned, so I should mention some positive cases here. So for example, if n is 2, this was kind of classical. I shouldn't used to do the Gelbart and Jacquet, that there exists such a thing. And if n is 3 and n equals 4, so this is a great success of the Langlands-Shahidi method, and this is due to Kim and Shahidi, and this was done by Shahidi. And a very important result. Yeah?
Second one is Kim.
Kim, I'm sorry, yeah, sorry. I meant to write. Yeah. Sorry. Okay, thank you. Yeah. All right, so this is actually, I should write Henry Kim, because when I was in Korea, I realized that 30 pages of the phone book are Kim. It's Henry Kim. I don't know his middle name. Maybe he all knows. All right, so it's a very beautiful theory here, and this is a result of what is called the Langlands-Shahidi method of L functions. And the point is, the thing that makes everything work is this thing called Converse Theorem, due to Cogdal and Piotrowski-Shapiro. And I should take a moment to say that Piotrowski-Shapiro really made an incredible series of contributions to the subject, and we're all very sorry he passed away during the past few months. And so, and he wasn't perhaps so well recognized for his important insights in the Converse theorem, I think. So it's very fundamental. And basically the idea is in the Langlands-Shahidi method, Langlands already, in his book on Euler products, noticed that a lot of interesting L functions appear. Right? I hope my wife agrees. Yeah, okay. All right. So since I don't have too much time, but I will just say orally, the Langlands method is to look at L functions, complicated L functions, like certain things that come up in this theory, and he realizes them as non-constant terms of certain Eisenstein series on a larger group. And here they have to use the... and then on the other hand, the Converse theorem says that if you know enough results about L functions, when twisted by smaller GLs up to n minus 2, then you can actually prove things are automorphic or modular, as the case may be. And luckily it works up to the symmetric fourth power here, but not beyond that, unfortunately, because you don't have any finite dimensional Lie groups whose Levy components contain all the GLs that you want. And the Cogdal PS theorem tells you if you have all the good properties of the L functions, then you will get something automorphic. So the basic idea here is somehow to always use some information. And I will maybe say in a few words, before I do that, let me try to say why what I wrote down over there is true. Maybe I'll just say it here briefly. And then I will come to the other results that one knows about elliptic curves in a few minutes. But let me first explain this theorem here. What is the idea of proof? So the idea of proof is that, so essentially you look at this lambda, so you look at Moss forms, so you look at Moss waveforms, but in L2 of the upper half plane modulo gamma, in this case, and you choose a certain basis. So what you can do is that there are these exceptional, so you can look at their eigenvalues, Laplacian eigenvalues. Lambda. So there is a famous conjecture of Selberg that lambda is greater than or equal to 1/4 if gamma is a congruent subgroup, which is what we are looking at. And it's certainly false if it's not a congruent subgroup. And the example, one of the examples I gave is really for lambda equals quarter. So we know the lambda equals quarter exists. So you have these other things. So the question is, do they exist in the other cases? So what one does is that you write lambda as, right here. You write lambda as s times 1 minus s. Then of course you can check that if lambda is less. So these are called the exceptional eigenvalues that you have. If it's SL2Z, you know that there exist no exceptional eigenvalues. This is equivalent to saying that S is between 1/2 and 1. So, okay, so you have these things here, and what you can do is that by using, if I use the one at the back, I think I'll hide it. So, okay. Okay, so what you can do is by using a trace formula, like Kuznetsov trace formula, which is the same thing as relative trace formula in the sense of Jacquet on GL2 relative to maximal unipotent subgroup and a non-trivial character. So if you write down the Kuznetsov trace formula, then for this number p of x, you get the following formula, which is very short. So it's partly why I'm giving it, because once Sayre told me that it's okay to give a general talk and not prove anything, but you need to prove something. So this is the only thing I will prove. So if you look at so this is 2 or 1, depending on whether -1 is in the group. So this is gamma of, so let's look at the exceptional eigenvalues. Let's call them lambda 1, etc. So these are exceptional eigenvalues. If you write Sj minus 1/2, take gamma of Sj plus 1, and then here you take, this gives you an orthonormal basis of the eigenforms, and then you take Uj of W bar, and then you get x to the Sj, and then you get x to the 2/3 here. And this 2/3 comes from Eisenstein series. So you want to prove somehow that, then you certainly have the x term, because you have the constants in there. So when Sj equals 1 appears, because that you have the constants in here. So therefore, what you have to do is to prove the theorem essentially suffices to show that, so this Sj between 2/3 and 1 So this does not occur. Okay. So that's the same thing, if you like, between lambda. So this means that the lambda is not between 0 and 2 nines. Not possible. And every time, this was really one of the bases of Langlands' principle of functoriality, is when you consider an automorphic form on a group, like the simplest case of a Moss form on GL2, it's all of its, knowing all the higher L functions for the higher representations of the dual group, kind of give all the information you want. It's kind of not good to think of one L function as being attached to a modular form. You have to consider a whole family. And so therefore, now it turns out that the existence of the symmetric. So for any such lambda, you have a pi lambda, which is appearing in the L2 cusp of H modulo gamma, which is an irreducible unitary representation that this Moss form generates, actually. It's an irreducible unitary representation, if you like, of SL2R. And you can also think of it adelically, but in any case, existence of the sim cubed of pi lambda as a modular or automorphic form on GL4 implies that that lambda is greater than or equal to 66 over 289, which is hopefully greater than 2 nines. So the earlier, so if you like, 66 over 289 is something like roughly 0.222. So any okay, no, and I'm sorry, 228. That's right. Whereas, no, I computed it. That's why I'm saying this is roughly 0.222. This is how I know. I had to do this computation. Okay. Okay. So the reason I'm trying to make this point is that earlier, Lowell, Rudnick, and Sarnak had proved using essentially symmetric square and various beautiful tricks that they had proved actually the minimal eigenvalues. It's like they had proved that lambda is greater than 0.21. So somehow that's not sufficient. You have to just get up to sim cubed. But afterwards, knowing the higher symmetric powers are automorphic actually has no bearing on this problem. Which is kind of nice. So, because in practice, you don't have information. It's very hard to expect in general everything. But this is a nice problem. So I thought I would mention it. Okay. All right. Okay, so I should mention that there is work of I should also mention that when pi is associated to an elliptic curve or over Q, much greater work, starting with the work of Wiles and Taylor-Wiles and various people, we know that every elliptic curve over Q is associated to F pi, which is a holomorphic new form of weight 2. And in this case, one does know it by a theorem of Taylor Harris, Michael Harris, I should say, since they're so Joe Harris. So and Clausel and Nick Shepard-Barron. That at least at the moment, at least for n minus n odd, even dimensional, sim n pi, we know is not necessarily automorphic. This is potentially automorphic. I think that for n even as well, perhaps Richard knows that. I think
n even is fine if you use Fukushina's
yeah.
recent treatment.
And there's a paper by Michael Harris in the yeah.
And you also need to resolve the value.
Right. Yes. Yeah. So anyway, as far as published works go, I know only this. And I have I think okay. So maybe I don't know. So here's sorry. Okay, I think okay. All right. So this is a great result, which is so. What does potentially automorphic means? That is, it is automorphic over totally real Galois extension. F. Okay. So it's a very beautiful thing, as you all know well, because there were lots of talks about it either a year or two ago about how this implies the Sauter-Tate. But I should say that also there's one other thing, as far as I could tell from the published works. There's also maybe you have to assume that this is maybe semi-stable, right? I mean, perhaps that also gets eliminated in the current thing. So this implies the Sauter-Tate, but I do have a reason for mentioning this. Okay, conjecture for E, which is really a beautiful result. And somehow the way the Sauter-Tate is proved is that using this and an idea of Brouwer, what they prove is that the L function of the symmetric nth of pi is the standard L function of sim n pi, or the symmetric. So Langlands would write this L as pi symmetric nth power. This thing here is holomorphic and non-zero in the real let me write it this way: real power if s equal greater than or equal to 1 in the unitary normalization. Whenever you have L functions, there are two normalizations. One depends on the weight, and one just depends on. There are lots of good reasons to do both. And actually, I think this is kind of one of those things in life that I find that it's better to use one in one case and another case. So it's a very beautiful thing, and it's a. So this is a very beautiful result, that it's holomorphic and non-zero. Okay. So I want to say one. Okay. Another. So functoriality, principle of functoriality is very amazing. It's related to many things, and so okay. One other thing I want to introduce, a personal note of interest, is that one of the one important, I would say very important case of functoriality is when you start with when you look at GLM cross GLM, then of course you have a map to GLNM, which is given by the tensor product. And so this is sometimes called the so essentially the important functoriality is if you start with the form on GLN and another one on GLM, then you expect some tensor product here. This should be an automorphic form on GLMN. And if one proves this, I think lots and lots of consequences will follow. It's a very powerful thing. Of course, you could ask about the direct sum, and that was solved by Lagrange. It's not trivial already. It uses this theory of Eisenstein series. But if you take this tensor product, it's very little is known. It's kind of very strange. So very little is known. If n, of course, if n or m equals 1, it's okay. It's just twisting by characters. It's not completely, it's not trivial, but it's okay. And then if I had something to do with this n equals m equals 2 case, then I could check this is okay. So essentially, if you use two ingredients, one is the Converse Theorem. In fact, Cogdell and Piatowski-Shapiro hadn't proved this precise Converse Theorem I wanted for GL4. So I bugged them till they proved it. Then I could use it. So it was very useful. But the second thing is using the triple product L functions. And I had to use some trick because even today, the triple product L functions related to 3 pi cross pi prime cross pi double prime is simply not fully understood, actually. So you have to use some tricks to do this. And then the next case, okay. I know that it looks like it's linear algebra. You can easily do it, but it's not because you have to. I know I was trying to explain this once to one of my colleagues, and he said, "Oh, it's just linear algebra." Sure, you can take a tensor product. And essentially the key point is this. If you take two automorphic forms or two automorphic representations, you can form the tensor product formally, and you will get an irreducible, admissible representation. But then you have to show that it appears in this cuspidal spectrum. That's why it's difficult, actually. So also when n is 3 and m equals 2, this is a beautiful theorem of Kim and Shahidi. And this actually is what was used actually to prove the sim cubed result, actually. So it's very important that you can do this in this case. And essentially the reason is that they take the symmetric square of one of the form on GL2 and then take a tensor product with the other pi prime also on GL2. And this allows them to use the Converse theorem and various things. And you prove this is automorphic, then you can use it because if you take pi itself, then you'll get sim cubed of pi plus pi twisted by its central character, and plus in the Lagrange sense. So you can deduce what you want. So the tensor product is very important. So I have an ulterior motive to tell you something I thought about a few years back with Hofstein. So the point is that one of the things that comes up, to backtrack a little, when you work with congruent subgroups, essentially you can make use of all the primes. And then you have all the various data of the trace of Eck operators, etc. And that's why it leads naturally to the adelic representations, and that gives you L functions very naturally. So what you can prove is that if you take some L function, so this is some L function with Euler product and functional equation, then and let's say it has a functional equation from relating s to 1 minus s, like the Riemann zeta function. And let's say that this is entire L function, or at least it's holomorphic near 1. Let's say it's entire. So so when you have an automorphic form, which is a cusp form, a theorem of Gaudemont and Jacquet says that the L function has all these properties. That's one of the basics things. Except in the trivial or highly non-trivial case of the Riemann zeta function. So, so the point is that the general Riemann hypothesis says that LS has no zeros outside the real part of S equals 1/2. So that's what it says. And then a few years back I tried to understand this as to, I was convinced that somehow the Langlands program should give some information about this. So what does Functoriality say? I mean, so the point is that the question is, what does Functoriality say about this, right? So about GRA, not much, but it says something a little bit. So the point is that one could look instead of looking for. So essentially, it says that in the critical strip there are no, to the right of 1 there are no zeros. So in the critical strip there could be lots of zeros here. But of course people have looked at zeros that are very close to 1, which are called Siegel zeros, and now also called Landau Siegel zeros. And so you can ask, are there zeros close to 1? Are there real zeros close to 1? And this is kind of very, so the first thing I was trying to think is that, is this somehow implied by Functoriality? Because it gives a lot of information about S equals 1 and to the right. So does it give anything here? So what Jeff Hofstein and I proved is that, so if the tensor product Functoriality holds for GLN cross GLN, then for every n, this is kind of a strange thing, for every n greater than 1, then that there exists no Siegel zeros for LS pi. So I can be more precise about what it means to be zeros close to it. It's kind of really interesting that it says something. It doesn't say a whole lot, maybe not satisfying to people, but, and for n equals 1 it fails. So I think it's kind of nice because, oh yeah, thank you very much. Pi is a cusp form on the GLN. This can be over any number field actually, or any global field. So essentially it says that there, and it's kind of a very strange thing. If you think about it, the reason is somehow, if you think of pi that corresponds to a Galois representation, V, say, the reason n equals 1 fails is that somehow when you take V tensor V, you get, you need to have some irreducible constituent which is not V itself or the trivial representation. That's what makes everything work. So when V is the trivial representation or a quadratic character, it doesn't work. Every other case it works. So it's kind of strange. It's kind of, so in a sense, so therefore this doesn't touch the case that many people are interested in, like the Gauss's class number problem, because that has to do with the quadratic Dirichlet character. So it's very interesting that you can, but I still thought I should mention it because Functoriality is very powerful. And in a way, in our proof, what we use is essentially the symmetric cube L function is holomorphic to something like 1/2 to the right. And in fact, there were results with Bump and Friedberg and Ginsberg, but didn't quite have what we needed. And then Shahidi's results were enough. So you didn't really need this in our case. So I guess what I mean is, I should have said here, for n equals 2, so this is unconditional. I mean, it's still conditional on the same thing, but you can check the condition. Okay, so it's kind of nice that if you take an L function of an elliptic curve, for example, you don't have any z equals zeros. I haven't found. So the reason I thought I would mention it is that, in fact, if you use this result of, in fact, if we combine, one combines this with the result of theorem of Taylor. What I mean is this approach. It's not. So in fact, what we do is there are really many different ways you can prove this, and if you combine this with the theorem of Taylor, Harris, and sorry, I just realized that I'm not doing things alphabetically. That was never my strength. Also, but also it looks like there's one extra name. Okay, so if you combine them, then one can show that if you take just this sim n of such a pi, remember, for e pi attached to an elliptic curve, you could prove that this thing here has no real zero near s equals 1. So you don't need it's not conditional. And potential modularity is sufficient. And essentially it's because you can use the Aramata-Brouwer theorem, which expresses the augmentation representation of the Galois as a positive integral linear combination of monomial characters. If you use that and then our method and feed it into this, you get something about the original L series. Okay, I think I'm running out of time, unfortunately. I haven't even started the trace formula. That was going to be the main part, but okay. Oh, okay. All right. Actually, when I first started writing this, I consulted with Arthur, and I called him yesterday, or day before yesterday, and told him, Oh, no. Oh, shoot. Okay, I should stop. Yes, sorry about it. I'm very sorry about the trace formula not being here. It's very important. Yeah, okay.
Well, maybe time for a quick question.
Yeah?
Maybe you can say one word, if you could demystify the connection between the number of points in a circle
Yeah?
and eigenvalues. I'm saying too much about the trace formula.
I only see it from using this trace formula. And essentially the trace formula, if you like, each Sj corresponding to the exceptional eigenvalue gives you a power of x there.
Right.
Yeah.
How does the number of points in the circle appear?
How does...
So what you
I mean,
do
it's
is
a...
sum over the lattice points.
Right.
And then by
Somewhat.
you take, so he's counting the number of lattice points in the circle. So you
Right.
take the favorite indicator of the circle, and you sum that over the lattice points. That's the number of lattice points. And then by some summation of the trace formula,
Yeah.
Kuznetsov trace formula, you can express it by sum over the spectrum of the Laplacian. And then the analysis will be done.
Okay.
Okay, anything else?
Yeah. In a sense, trace formula is a souped-up Poisson sum formula. Okay.
Any other questions? Well, let's thank speaker Ken.